Welcome to today's lecture, which is going to be on introduction to tensors. So, following are the contents of present lecture. We will start by first discussing what is meant by a vector. Okay. Once we have defined what is a vector, we will go into discussing the different ways of denoting a tensor, okay, which are used to denote tensors, which are direct notations and indicial notations. This will be followed by discussion on range and summation convention, which are used, and then we will discuss some rules for indicial notation representation of tensors. Followed by this, we will look into two important concepts in tensors, which is Kronecker delta and permutation and alternator symbol. Then we will look into what is meant by a second order tensor, okay. And then we will look into some of the operations that can be performed using second order tensors, which is sum of two tensors, product of tensors, inverse of tensors, transpose of a second order tensor, what is meant by symmetric, skew symmetric and orthogonal tensors. Finally, we will end this lecture with decomposition of a second order tensors. How can you decompose a general second order tensor into different ways? Okay. So, let us start. So, before we can discuss on what is meant by a tensor, first it is worthwhile to look into the question of what is actually meant by a vector. Okay. So, remember that tensors, why we should focus and why we should devote our time on reading about tensors. See, tensors are the language of continuum mechanics. Okay. Just like to speak, to interact with another human being, you need to know the language with which you can speak to the other person. Similarly, to understand, so for say you want to speak to continuum mechanics, you want to speak continuum mechanics, you should learn the language in which the continuum mechanics works. Okay. So, this language is nothing but the language of tensors. Okay. So, to have a very good understanding of continuum mechanics and by its implication computational continuum mechanics, one needs to have very sound understanding of tensors and tensor analysis. Okay. So, coming back to our question, what is meant by a vector? Okay. So, a vector from our school days we know was defined as something which has magnitude and has a direction. Okay. But not everything which has a magnitude or a direction can be classified as a vector. Take for example, a book. Okay. So, a book for example, has a direction. You always read book from one side to the another side, from top to bottom. There is a procedure. You cannot read a book the other way around. Okay. And also book has a weight. Okay. So, you cannot assign, you cannot say that book is a vector. Okay. So, that definition of vector that we have studied in our school is no longer fit. Okay. So, we need to look into another more involved definition of a vector. So, a vector follows the triangle law of vector addition. Okay. That is what I have written here. Vector follows the triangle law of vector addition. Okay. So, when two vectors are represented by two sides of a triangle in magnitude and direction taken in the same order, then the third side of a triangle represent the resultant of two vectors. Say you are given two vectors A and B. Note that I have put an underbar below the symbols A and B. Why? I have put this because I cannot write bold. Okay. When I am writing, I cannot write bold. So, there is a convention that I will put a underbar. Okay. The other way is you can, as we used to do in school, you can put an arrow. Okay. But in the continuum mechanics courses, we do not put arrows, that is not usually followed. what is usually followed is we put a underbar. Okay. So, given two vectors A and B, the resultant of these two vectors A plus B will be another vector C. So, what will be C? This is visible in this picture. Okay. So, you have a vector A, okay, and you have another vector B. Okay. So, now you put the vector A and then you put the tail of vector B at the tip of vector A, and then the resultant vector C will be nothing but a vector which extends from the tail of vector A to the head of vector B. Okay. So, this will be your vector C. Okay. So, any vector which satisfy this triangle law of vector addition will be called as a vector. But what is the drawback here? The drawback is you need at least two vectors to define, okay, what is meant by a vector. Okay. So, you need two vectors. Okay. So, this is what is called the, and we will come to it in the current lecture some point later, it is called the operational approach. Operational because we are operating on two vectors, you are operating on two vectors A and B to get a third vector. So, this is called the operational approach. Okay. So, in operational approach you always need more than one quantity to define another quantity. Here you have two quantities, two vectors, you add to get a third vector. Okay. So, we like to define vector in much more refined way. Okay. And for this we come to how the components of a vector transform when the coordinate system changes. Okay. So, in this present course we are going to deal with only Cartesian coordinate system, okay, because of the number of lectures being limited, we will not deal into curvilinear coordinate systems, we will only fix our attention to Cartesian coordinate system. So, as you can see here, you have a Cartesian coordinate system shown here x 1, x 2, x 3 in bold black lines, okay. And then the unit vectors along the directions x 1, x 2, x 3 are denoted by E 1, E 2 and E 3. Okay. This has to be E 3. So, these vectors E 1, E 2, E 3 are called the basis vectors. So, what are E 1, E 2, E 3 there? So, E 1, E 2, E 3 are like your I, J, K that you would have studied in your school days. Okay. So, E 1 is a vector, okay, because it is a vector we put a one bar below it. E 1 is a vector which is entirely along the x 1 axis. So, what are the components of this vector? And E 1, E 2, E 3 are unit vectors. So, the component of this vector are 1, 0, 0. Okay. Similarly, the components of vector E 2 are 0, 1, 0 and the components of vector E 3 are 0, 0, 1. Okay. So, you can see these are nothing but your unit vectors I, unit vector j and unit vector k. Okay. So, we use, instead of using the notations I, j, k, we will use E 1, E 2, E 3. We will come to it later when we are discussing about the summation and range convention, why this is helpful. Okay. So, once we have this, so these E 1, E 2, E 3 are called the basis vectors. Okay. Now, you have a vector v. Okay. You see here there is a vector v which is in this represented by this arrow, yellow arrow. Okay. Now, you can write this vector v, okay, as v1 e1 plus v2 e2 plus v3 e3. Okay. So, the first term, okay, you have v1 is the component of the vector v in the e1 direction, v2 is the component of the vector v along the e2 direction, and v3 is the component of the vector along the e3 direction. Okay. So, the complete vector becomes the sum of these three vectors along the x1, x2, x3 direction. In short, you can write summation v I e I, where I goes from 1 to 3. Okay. So, this is what we call as unprimed system. Now, we rotate the coordinate system. Okay. This is shown here. Okay. You can see this is shown here by this red arrows. So, what you have done now, you have rotated the coordinate system. So, the new system now becomes x1 prime, x2 prime and x3 prime. Okay. When the coordinate system is rotated, the basis vectors e1, e2, e3 are also rotated, and they become now e1 prime, e2 prime and e3 prime. Okay. Now, you can see we have just rotated the coordinate system, we have not rotated the vector itself. Okay. Now, in what is called the primed system, okay, one which is obtained by the rotation of the original coordinate system, we can write the same vector in terms of its components v1 dash, v2 dash, v3 dash along the x1 dash, x2 dash and x3 dash directions. In short, we can write summation I equal to 1 to 3 v I dash e I dash. Now, there is nothing which has happened to the vector remains there itself. What has happened is we have rotated the coordinate system. Now, the question is, can we find a relation between the components of the vector in the primed system, which is v I, and the unprimed system, which is v I dash. Okay. So, we want to find out our relation between the components of the vector in the prime and the unprimed system. So, how can we do that? So, to do that, we first see that E1 dash, E2 dash and E3 dash themselves are vectors which can be written in terms of the basis vectors E1, E2, E3, and this is given by following relation. Okay. You can see Q11 E1, Q21 E2, Q31 E3 is E1 dash, E2 dash is Q12 E1 plus Q22 E2 plus Q32 okay, E3. Like this, we can write all the three basis vectors in the prime system in terms of the basis vectors of the unprimed systems. Okay. So, in short, I can write Ej dash as summation Qij Ei. Okay. I can write Ej dash as Qij Ei, okay, where this quantity Qij is nothing but the dot product of the basis in the Ei of the unprimed system with the basis Ej dash in the primed system. Okay. So, because both Ei and Ej okay, are unit vectors, this would be nothing but the cos of the angle between Ei and Ej dash, okay, because you know that A dot B is nothing but magnitude of A into magnitude of B into cos of theta, where theta is the angle between the vectors. Okay. Now, because if A and B are both unit vectors, therefore, the magnitude of both the vectors will be equal to 1, and then cos theta okay, is A dot B. So, ei dot ej dash is nothing but the cos of the angle between the basis vectors ei and ej dash. Okay. Similarly, you can turn this expression the other way around. Can you write ei in terms of ej dash? Yes, you can do that, okay, because ei themselves are vectors. When you look from the prime system, you can see ei's where I goes from 1 to 3 as vectors. So, you can express them in terms of the basis vectors of the prime system given by following equation. Once you have this equation, we have tools in our hand with which we can express the components of the vector v. Okay. We can find the relation between the components of the vector v in the unprimed and the primed system. Okay. To do that, we start with this definition of the vector. Okay. Now, you know that the component of a vector is nothing but the vector dotted with the basis vector along that direction, okay, the unit vector along that particular direction. Now, so v1 would be nothing but the vector v dotted with e1, right. You will get the component of the vector along the e1 direction. v2 will be v dot e2 and v3 will be v dot e3, right. So, once you have this, now you know the relation between ei's and ej dash. Okay. This we saw in the previous slide. You can substitute this expression for ei in the expression or equation 1. Okay. So, once you substitute that, okay, so vi is v dot qij ej dash. Okay. So, this I can write as sigma qij v dot ej dash. Now, what is v dot ej dash? It will be the component of the vector v along the jth direction in the prime system, which is nothing but qij vj dash. Okay. So, this is what we get as part of our equation 3. Okay. So, we can relate the component of the vector in the unprimed system, which is vi, to the components of the vector in the primed system, which is vj dash. Okay. So, we can now express this relation in the matrix form, okay, as vector v equal to some matrix q times vector v dash. Okay. So, this is nothing but v1, v2, v3. Okay. So, I am writing this equation 4. Okay. We will have q11 like this, we will have q33. This will be a 3 by 3 matrix, v1 dash, v2 dash, v3 dash. So, now you have related the components of the vector in the unprimed system to the component of the vector in the primed system. Okay. And q is the matrix, you know how to compute the components of this matrix q, okay, which is nothing but the cos of the angles between the basis vectors. Now, we want to find out the relation between v dash and v. Okay. So, to do that, we again can start with vj dash, okay, as v dot ej dash, and now we know ej dash is nothing but summation qij ei, and using the procedure that we just now discussed, you can show that the relation between the components of the vector in the unprimed system and the primed system. Okay. So, unprimed system, the components of vectors can be written as vector v, and the primed system we have v dash. So, v dash will be q transpose v. Okay. So, you will have v1 dash, v2 dash, v3 dash equal to, so this matrix which is here transpose V1, V2, V3. Okay. So, now this is what. Okay. Now, you can check this relation with our definition of a vector which was summation vector which satisfy the triangle law, okay, of vector addition here. So, there you needed two vectors, here we just can do, we need only one vector v, and using that you can derive the relation. Okay. So, very important thing to note is that quantities which follow the transformation law, okay, rule. Okay. So, by given by equation 4, okay, by equation 4 and equation 8 are called vectors. Okay. So, any quantity if you are given and you are asked to show that whether that quantity is a vector or not. So, what you have to do? You have to show that components of that quantity transform according to the relation given by either equation 4 or equation 8. We frequently use equation 8, okay, because the vector v is given to us. Okay. And now, we start with vector in the prime system and we will try to show that the components of the quantity transform according to equation 8. If they transform according to equation 8, then that quantity will be called a vector. If that quantity does not, the components of that quantity does not transform according to equation 8, then that quantity will not be called a vector. Okay. So, before we discuss more, we will try to see what is meant by direct notation and initial notations. Okay. So, first we look into direct notation, which is also called the invariant notation. Okay. So, it is important to point out here that tensors are physical quantities. Okay. They represent physical quantities like mass, velocity, stresses. Okay. So, because they are physical quantities, they should not depend on the coordinate system, okay, because coordinate system can vary from person to person. Okay. One person can have one coordinate system, another person can use another coordinate system. But for example, mass will not change with the coordinate system, the velocity will not change with the coordinate system. Okay. So, the tensor should not change with the coordinate system, okay, in some way. Okay. But we do define coordinate system. Okay. So, there should be a way to represent the tensors and their operations without referring to any particular coordinate system. Okay. So, this kind of notation which is used to represent tensors and their operations without referring to the coordinate system is called what is called the direct notation, okay, or the invariant notation. Okay. So, direct notation provides us symbolic representation of tensor operation. Okay. So, when you write the operation between tensors in direct notation, it is symbolic representation. However, it does not tell you how these operations will be actually performed. Okay. So, we look into some examples. For example, a velocity vector. Okay. So, when we are typing, okay, on a computer is usually denoted by symbol V, which is bold. Okay. However, when we write by hand, because we cannot write a bold letter, what we do, as I told earlier, we will write symbol V and then put a single bar. Okay. We will come to it later, why 1 bar. Okay. Stress, for example, when it is typed on a computer, we will put sigma, which is bold. However, when we are writing, the direct notation for stress will be sigma and then there are 2 bars below it. Okay. We will come to it, why we are putting 1 bar below velocity and 2 bars below the stress sigma. Okay. But that is how direct notation is used. Okay. So, there is another notation which is called the indicial notation. Okay. So, when you have to operate upon the tensors, when you have to do certain operations, okay. So, then that time you will utilize a certain coordinate system, and then you will represent the components of tensor with respect to those coordinate system. Okay. So, the explicit representation, okay. So, the explicit representation of tensors in terms of their components is what is called indicial notation. Okay. So, these indicial notations are used when tensors operations involving numerical values are used. Okay. When you are doing some numerical computations, you will use indicial notations. For example, the trace of a stress tensor when you are doing finite element computation. So, when you have to do trace of a stress tensor, you have to use indicial notation. Okay. So, in indicial notation, the tensor's spatial directions are denoted by indices which are generally attached as subscript to the symbol. Okay. For example, mass is a scalar quantity. Okay. So, there is no index subscript which is associated with it. Velocity vector, for example, there is one index subscript when we are writing velocity vector in indicial notation. So, there will be one index which is attached as a subscript. Stress tensor, for example, has two indices as subscripts. Okay. So, the number of indices, okay. So, the number of indices which are attached as subscript to the tensor when you are using indicial notation is what is called the rank of the tensor. Okay. And what will the range? Okay. So, the range of this index, okay, for velocity we have I, and tensor we have I and j, two indices. So, what will the range? What values will these indices take? So, that will depend on the dimensionality of the space. For example, in 3D I will take values from 1 to 3. Okay. Similarly, in 3D the stress tensors both I and j will take values 1 to 3. So, stress tensor in 3D will have total 9 components, sigma 1 1, sigma 2 2, sigma 3 3, all the way up to sigma 3 2, okay, like this. Okay. There will be total 9 components. Okay. Now, we come to what is called the range and summation convention. Okay. Now, to study about the range and summation convention, it is important that instead of going to theory, we will start with an example. Okay. And this will make you understand better how to write expressions using indicial notations. Okay. Because when you are doing computations, okay, and we are simplifying expressions, you will be mostly writing in indicial notation. Once you have done the indicial notation, you will transform the indicial notation back to the direct notation. Okay. So, suppose you are given a system of algebraic equation, n equations are given to you which are shown here. Okay. Now, if you have to write these equations many a time, okay, it will be very cumbersome and very tedious to write all of these equations every time that you have to do certain computation. So, would not it be better if we can somehow condense all these equations into one small expression. Okay. So, this can be done using what is called the range and summation convention. Okay. So, the first step that you can do is we can write these equations in a compact manner given by a I 1 x 1 plus a I 2 x 2 all the way up to a I n x n equal to b I, with the i's taking all the values in the range 1 to n. Okay. Now, n can be anything, okay, n can be 10, n can be 3, n can be 1000, whatever. So, I will take all values. Now, you can see instead of these n equations, we just now have one equation, okay, and this is given here. Okay. Now, what we can do? We can drop this line, okay, which we have to explicitly mention, okay, and we can just write the expression, okay, here, with the understanding that I will take its value in the range 1 to n. We need not specifically or explicitly tell that I will need to write that I will take values 1 to n. Okay. Just writing this expression suffices. So, this is called range convention, okay, because I takes value in its range 1 to 3, the range, that is why the name range convention. Okay. So, this index I is what is called the free subscript or the free index at this, because it is free to take values in its range 1 to n. Okay. So, somebody can ask why I, can I use some other index? Very well, you can use another index. For example, if I use j, I can write aj1 x1 plus aj2 x2 all the way up to bj. The meaning of the expression remains same. Okay. Now, I can further compress this expression. I mean, this expression over here is still long. I mean, it will be tedious to write. So, what we can do? I can use the summation sign and I can write summation j equal to 1 to n a I j x j equal to b I. Okay. Using this, I can write the top expression in a compact manner, but still there is a summation symbol. So, I can just compactly write this expression by dropping the summation symbol. Okay. So, this summation symbol over here can be dropped and I can simply write a I j x j equal to b I, with the understanding that whenever there is an index which is repeated, then there is a summation which is implied. Okay. So, j for example is repeated here. So, I can understand there is a summation which is implied over j. Okay. So, this convention is called the summation convention or Einstein summation convention. Okay. So, j here in this expression over here, j is called the dummy index. Okay. J is the dummy index or the repeated index. Okay. And a I j x j is called a, so each product term in an expression is called a symbol group. Okay. So, there are two symbol groups here, a I j x j and b I. Okay. So, each product term in an expression, it will be a symbol group. So, anybody can ask why j, can I use some other symbol? Yes, you can use, instead of j you can use k. Okay. So, you can write instead of a I j x j, you can write a I k x k equal to b I, and this itself is identical to the previous expression and its valid expression. Okay. So, a particular choice of index for the dummy subscript is not very important. Okay. Now, you also should note that no subscript is allowed to appear more than twice in any symbol grouping. Okay. So, you cannot write a I x I equal to b I. This is not a valid expression. Okay. You should note that you cannot write an index more than twice. Okay. So, this brings us to some example. The first one is, can you expand? The first one is a I b I, and I want to expand this expression. Okay. So, I, for example, here is a repeated index. Okay. And there are no free index here. Okay. So, I is a repeated index. So, by a summation convention, it is implied that there is a summation which should be carried out over I, and I should take all values from 1 to n. If something is not mentioned, then we usually take the range as 3. Okay. So, I will go from 1 to 3. So, I can write this as, this actually means I equal to 1 to 3 a I b I, which is nothing but a 1 b 1 plus a 2 b 2 plus a 3 b 3. Okay. So, there is one single expression which is a 1 b 1 plus a 2 b 2 plus a 3 b 3. So, the next example is sigma I k n k. Okay. So, we note here that I here is a free index, okay, and k here is a repeated index. Okay. So, I will take values in its range 1 to 3, okay, and k will take its values in its range 1 to 3. As I mentioned, if nothing is mentioned, we will take that the range goes from 1 to 3. Okay. So, since I is a free index and I takes value 1 to 3, so this is basically 3 equations: sigma I k n k, sigma not I k, sigma 1 k n k, sigma, okay, sigma 2 k n k and sigma 3 k n k. Now, each of this expression you can further use the summation convention to write sigma 1 1 n 1 plus sigma 1 2 n 2 plus sigma 1 3 n 3. Okay. So, the rest too I leave it to you. So, you can write the other two expression. So, there are total 3 expression, each expression has 3 symbol group or the product terms. Okay. Now, we go the other way around. Given an expression a 1 1 plus a 2 2 plus a 3 3, okay, I can write summation I equal to a I, and using summation convention I can drop the summation symbol and I can write simply a I. Okay. So, that is my expression in the indicial notation. Now, the second expression is a 1 square plus a 2 square plus a 3 square. Okay. So, this I can write summation I equal to 1 to 3. Now, one thing which is never done when writing in indicial notation is we never write the power. All these terms have a power 1. Okay. So, here we have been given power which is 2. So, basically this expression is nothing but a 1 into a 1 plus a 2 into a 2 plus a 3 into a 3. Okay. So, I can write this as a I into a I, and this is nothing but a I. Okay. So, as I mentioned, we do not write power. Okay. All terms have power 1. So, we do not write a I square, we have to write a I into a I. Okay. Now, the last expression is you have say a matrix A and another matrix B. Okay. These are 3 by 3 matrix. So, product of 2 will be a 3 by 3 matrix. Now, suppose you have to write in the indicial notation. Okay. So, this is written as A I K B K J. Okay. So, now for the last one I leave it to you. You write explicitly all the expression, all the terms for product of matrices A and B, and finally reduce. So, if you have A as 3 by 3 and B as 3 by 3, you will have 3 equations with each equation having 3 terms. Okay. You will have 3 expressions, and you should be able to compress using the range and summation convention the 3 expressions into what I have written here, A I K B K J. Okay. So, this expression has 2 free indices which are I and J, okay, and there is one repeated index which is K. Okay. So, with this we move to our rules for indicial notation. So, when you are using indicial notation, there are certain rules that you have to follow, and these rules are stated as 5 points here, okay, in this slide. The first point is the lowercase Latin subscripts take the values in the range 1 to n, where n will be equal to 2 for 2D problems and 3 for 3D. Okay. A given index may appear either once or twice in a symbol grouping or a product term. Okay. So, every expression will have product terms which are also called symbol groupings. So, a given index can appear once or it can appear twice, not more than that. If it appears once, the index is called a free index. Okay. and if it appears twice, it is called a dummy index or a repeated index, and then summation will be implied. The same index may not appear more than twice in the same symbol grouping. So, in one symbol grouping, a particular index cannot occur more than twice. Okay? So, either it can be a free index, which is it can occur once, or twice, which is then it means that that index is a repeated index or a dummy index. So, all symbol grouping in an equation must have the same free subscript. Okay? So, it may happen that your expression is long and you have multiple product terms, okay? But in each product term the free index should be same. Okay? In the first product term, if the free index is I, in the second product term also it will be I, the third product term also it will be I, like that. And you can have as many free index as you want, but it can occur only once within each product term, and for all the product terms it can the free index should be same. Okay? And the free and the dummy indices may be changed without altering the meaning of an expression, provided that one does not violate the preceding 4 rules. Okay? You can interchange the free and dummy indices, you can make I equal to j, j equal to k, whatever, j equal to I, but you should keep in mind that the first 4 rules should not be violated. Okay? So, with this we move to few examples, and there are 4 examples, and we wish to identify whether these expressions are valid or not. The first is Tij, Vi, Vj, whether this expression is valid or not. So, we can see that both I and j, so there is one symbol grouping here, only one product term Tij, Vi, Vj, and both I and j are repeated twice. There are 2 i's and 2 j's, and there are no free indices. Okay? So, all the 4 rules that we mentioned in the previous slide are valid. Therefore, this is a valid expression. Now, we come to the next expression, which is Aij equal to Bikl Cjl dk. Here we have 2 product terms, okay, or 2 symbol grouping. First is Aij and the another is what is on the right hand side. So, we count the number of free indices. Okay. So, I occurs, so in the first symbol group I occurs once and j occurs 1. Okay. So, we should check in the second symbol group whether we have I and j, and they should occur only once. So, I occurs in the subscript of B once, fine enough, j occurs in C once. Okay. So, that is fine. Now, we have k which occurs in the second symbol grouping twice, and we have L in the second symbol grouping which occurs twice. Okay. So, we have free indices I and j occurring in all the symbol groupings, and the repeated index k and L in the second symbol group repeated twice. So, all the 4 rules are followed. So, this expression also is a valid expression. The next expression is sigma ij equal to dij kl epsilon kl. This is similar to the second example. Here also I and j are the free indices, you can see here, and k, l, n are the dummy indices. Therefore, this also is a valid expression. So, the last expression now is alpha k equal to epsilon ij k delta ij plus dij kl fi g jl. Okay. Now, this expression has 3 symbol groupings or 3 product terms, one on the left hand side and 2 on the right hand side. Okay. So, if you look into the first term alpha k, so k occurs here, okay, once. So, k has to be a free index, okay, obviously, because it occurs once in the. So, we should check in the other 2 symbol grouping whether k occurs once. So, in the second expression we can see k occurs here, and here also k occurs here only once. Okay. So, that is valid, k is a free index. Now, we check for whether we have the repeated index occurring properly. So, I and j in the second symbol grouping occur twice. Okay. So, that is fine, they are repeated index. In the second symbol grouping on the right hand side, I j k l, okay. We have I j k l, also we have I, we have j and we have l. Okay. So, you can see here, okay. So, k l occur and now you have m. Okay. So, in the second expression also you have I which is occurring twice, j which is occurring twice, you have l which is occurring twice. Remember, k was a free index. Now, the only index which is left is m, which is occurring only once. If an index occurs only once, it has to be a free index. So, it should occur in the other symbol group, but if you check on the other two expressions, there is no m involved. Okay. So, because m is a free index for the third expression, but it does not occur in the other symbol grouping, therefore, this is not a valid expression, because m being a free index in the second expression is not present in all other terms. Okay. So, if you look into these examples, the first three are your valid expression and the last one is your invalid expression. Okay. The next concept that we look is called the Kronecker delta. It is named after the German mathematician Leopold Kronecker, and it is a function of two variables, usually just the positive integers, and the value of this function is 1 if the indices, okay, if the values, if the variables are equal, and 0 otherwise. Okay. A Kronecker delta is usually denoted by the symbol delta followed by two indices I and j. Okay. So, if I is equal to j, then the value of delta I j will be equal to 1, and if I is not equal to j, then delta I j will be equal to 0. Okay. And I and j will take values from 1 to 3. Therefore, delta 1 1 will be equal to 1, delta 2 2 will be equal to 1, and delta 3 3 will be equal to 1. Delta 1 2 equal to delta 2 1 equal to delta 3 1, okay, equal to delta 1 3 equal to delta 2 3 equal to delta 3 2 will be equal to 0. Okay. So, you can see if the indices are repeated, if I is equal to j, then we have the value of Kronecker delta which is 1, otherwise it is equal to 0. Okay. So, in linear algebra, the elements of identity matrix can be written in this form delta I j. Okay. So, I, an identity matrix of order 3 will be 0 1 1 0 0 0 1 0 0 0 1. Okay. So, you can see when row is equal to column, when I is equal to, so if you consider i's as your rows and j as your column. So, when I is equal to j, you have the value, okay, as 1, okay, sorry, the last one should be 1 0 0 1. Okay. So, for 1 1 2 2 and 3 3 you have value of identity matrix which is equal to 1, otherwise it is 0. Okay. So, the initial notation for a identity matrix is nothing but delta I j. Okay. Also, the dot product of any two basis vectors E I and E j, E I E j can be anything E 1, E 2, E 3. Okay. So, E I dot E j will be nothing but delta I j in Cartesian coordinate system. So, if you take I equal to j equal to say 1, so E 1 dot E 1 will be nothing but 1. Okay. But E 1 dot E 2, I and j, I is 1, j is 2. So, E 1 dot E 2 will be equal to 0, because cos of the angle between E 1 and E 2 is 90 degree, therefore, cos 90 is 0. So, E1 dot E2 is 0. So, you can write all this in a compact notation as Ei dot Ej equal to delta Ij. That is one other place where Kronecker delta shows up. The other places where it appears is when you are taking differentiation of a vector or a tensor with respect to its own component. For example, if you write del xi by del xj, it can be written as delta ij. Okay. If you have a second order tensor or a rank 2 tensor which has 2 indices, so del aij, del akl, aij correspond to ijth component of the tensor A. So, del aij by del akl will be nothing but delta ik delta jl. Okay. So, you remember that Kronecker delta plays a very important role during the manipulation of continuum mechanics expression in indicial notation. It will occur frequently and you have to use its property which is the substitution. Okay. So, Kronecker delta is used for substitution. Okay. So, now we look into 3 examples. Okay. Suppose you have been given the expression Aij delta Ij. Okay. So, this expression simplifies to Aj. How? Aij delta Ij. So, this has I as a repeated index. So, there is a summation which is implied and I will take value 1, 2, 3. So, we will write delta A 1 delta 1 j plus A 2 delta 2 j plus A 3 delta 3 j. Okay. Now, when j has value of 1, when j has a value of 1, then delta 1 1 will be equal to 1, but delta 2 1 delta 3 1 will be equal to 0. So, when j equal to 1, we are only left with A 1. When j is equal to 2, we are left with only A 2. When j is equal to 3, we are left with only A 3. Okay. So, you can see in this particular expression, Kronecker delta has replaced the index of A by j. That is called the substitution property. The property of j has been substituted. Okay. The I has been substituted with j. Now, if you have another expression Ajk delta Lj. Okay. So, this again you can see the common index between the Kronecker delta and A is j. So, the final expression will be this j from A will be taken out and L will go and take its place. So, the final expression will be A L k. Okay. So, you have A j k delta L j. Okay. So, what will happen? This j will be taken out, okay, and then this L will go and fill its substitute for that j over here, and then Kronecker delta also goes away. Similarly, the third expression Cij kl delta Ip. Okay. Here you have I which is repeated. Okay. We have Cij kl delta Ip. So, what will happen? I will drop off, okay, and P will go and take the place of I in C. Okay. So, you will have P here and then delta drops off. Okay. So, in general, the substitution property of a Kronecker delta in general can be written in this particular, is given in this particular expression, okay, where I is replaced by j. You can see I has been replaced by j, okay, where t is any nth order tensor. It can be vector, it can be second order tensor, fourth order tensor, whatever. The index which is common between the Kronecker delta and the term which is coefficient of the Kronecker delta gets replaced by the other index of the Kronecker delta, which is J here. Okay.